Hello, everybody.
Hi, Jason.
Hey, Mary Lou. Hey, Mark. Hey, Kevin.
Howdy.
How you guys doing?
Good. Good evening and welcome to the North Jersey Astronomical Group. This is the October meeting of the group, and we've got a nice speaker lined up for you. And for the members of the group, please do stick around at the end of the presentation. We will have a short business meeting following this presentation. But before we get to the presentation, we actually have a special surprise guest speaker tonight. Some of you may know David Levy, the rather well-known comet hunter. You may recognize his name from Comet Shoemaker-Levy 9, which he helped co-discover. And he's going to do a little poetry for us. He's going to start us out with some poetic words to get our meeting off to a good start, and then we'll go into our presentation. And so, David, if you'd like to take it away.
Well, thanks, Kevin, and I appreciate that. I am really happy to be here. Mark Zdarsky recommended that I come, and I thought that was a very good idea. Won't be able to spend the entire meeting here, but I'm really looking forward to hearing about the Hertzsprung-Russell diagram. When I was interviewing Bart Bok for a book I wrote about him decades ago, he said that Hertzsprung and Russell were kind of different astronomers. Russell came out, he said, with a big bass drum and started announcing his diagram, whereas Hertzsprung worked in pretty much isolation and essentially came up with the same thing at almost the same time. Anyway, for my quotation tonight, I'm going to quote from Shakespeare's Macbeth. And there was a speech that Shakespeare had to write for Macbeth as soon as Lady Macbeth is killed or dies. And the last line is, "The Queen, my lord, is dead." And Shakespeare is sitting there at his desk with his, I guess he doesn't have Windows Microsoft Word, but he's trying to think of, what am I going to write? What is Macbeth going to say? And then I like to imagine that there's a tap on his shoulder, and he turns around and there is God right behind him. And God says, "Will, take a break, get some coffee, relax, I got this." If you want to think that Shakespeare anticipated the story of space-time and the Hertzsprung-Russell diagram 400 years in advance, you may. And it's a little easier to imagine if I add two words. So I'm going to quote this and then add 2 words at the end. "She should have died hereafter. There would have been a time for such a word. Tomorrow and tomorrow and tomorrow creeps in its petty pace from day to day to the last syllable of recorded time, and then is heard no more. Out, out, brief candle. Life's but a walking shadow, a poor player that struts and frets his hour upon the stage, and then is heard no more. It is a tale told by an idiot, full of sound and fury, signifying nothing, signifying everything." Thank you, Kevin, and back to you.
Well, thank you, David. Nice little bookend for our day. We started out this morning watching William Shatner, Captain Kirk, going up into space, and we're ending the day with some poetic words from David Levy. Isn't that nice? And so I'm going to turn it over to Mary Lou West. She's going to introduce our speaker for tonight. And so, Mary Lou, take it away.
Hello. I also enjoyed very much seeing William Shatner go up into space, but mostly hearing him when he came back. He was just overwhelmed by the experience. He said basically Star Trek had not prepared him for this, and to go from a blue sky in Texas and up through the atmosphere, just whoosh, the atmosphere went past, whipped past him, and then he was in the blackness of space, and it was very black and it was full of death, and he was sort of frightened, but then they came back down. But he talked then several times about the little sliver of blue that envelops the Earth, and that is our atmosphere, and that's what keeps us alive. It was really an interesting experience to see him so affected by that.
Yeah, he got quite emotional there. You know?
He did, yeah. They said all 4 astronauts cried when they landed.
Right.
So interesting. Maybe we all could do it someday. I don't know. But anyway, so tonight we're going to hear a talk by one of my friends, Steve Quigley, from the Vermont Astronomical Society, of which I'm a member. My son and his family live in Vermont. And so when I go up to visit them, I can take part in this astronomical society. I've gone observing with them a couple of times, and picnics and that sort of thing. And of course, a lot of meetings, and had a really good time. And so made some friends. One of them is Steve. And among other things, Steve and I share a love of flying airplanes. Steve retired in 2002 from flying. I retired much previous to that. But at any rate, we're also both interested in how stars live their lives and what changes them from one stage to another. And the main theoretical way to understand the life of a star is through the Hertzsprung-Russell diagram. So Steve is going to tell us about that. Thank you, Steve.
Well, thank you, Mary Lou. I feel somewhat daunted by the sophisticated people in the audience tonight as a mere amateur. But I've always felt that if you're going to give a presentation to a group, you need to make a choice. Do you do something that you really know cold and you can pretty much do without much preparation, or do you pick a subject that interests you and try to study it intensely, and so you're not going to embarrass yourself as you start to talk? I've chosen the latter, and I'd like to, before I start, thank Mary Lou, because she was very gracious in helping a neophyte. When you're dealing with an astrophysicist and a retired pilot, the astrophysicist has got a lot more on the ball. But she was very gracious and helpful in the presentation. I guess I must have done okay since she asked me to do it again. But if I fall on my sword tonight, it's my fault, not hers. So I guess I need to reduce my screen slightly so I can see what I'm looking at here. And am I sharing?
Not yet.
Okay, I don't see the share button on up right now. Let's see, it's down below. Okay. I'll try to reset this a little bit. I do not see the share screen button anywhere on my screen.
It should be there somewhere because we did try it out earlier.
We looked at it earlier and I concur with you.
Bottom center, maybe?
Yeah, it's usually in the center. Sometimes, depending on how your device is set up, you have to move your mouse to the bottom of the screen, and it'll pop up. The little menu bar will pop up, and you'll see a little green button, share screen.
Well, I saw it earlier, but I don't see it right now. Doggone it. Okay, let me back out. No, that's ridiculous. Okay, I think I have now solved the issue.
Okay, good.
Let's see if we're correct.
Yep, it's starting.
Thank heavens.
There you go.
Okay. Stars have always held a special place in the human experience and imagination. We look up at the night sky and behold their beauty. We even sing nursery songs about them and wonder what they are. While we know that our own sun's light and warmth are essential to life on Earth, too often we regard the stars with a cold remove. But we're astronomers and we love to go out at night, and it's there we meet these old friends. Our ancestors did the same thing, and they found names for the groupings of stars. Let's see if we're going to advance. Come on, baby. I am embarrassed. Okay, let me see if I can back out of this one more time. Well, I don't understand why it's not functioning right now. If you'd like to do something else, let me transfer over to my other computer, and we'll see if we can get that one to work, because we seem to be locked up now.
Uh-oh.
Um,
Let's see if we can, let me stop the,
Why don't you stop and let me restart? It seemed to be functioning 1 minute ago, but
let's see, can I, that's me.
okay. That's me. Shall I try again?
Yeah, try it again.
Well, okay. Well, I guess I can do it with a cursor. Okay. Meanwhile, back to the stars. We know them as constellations, and we know many of them. We recognize asterisms, smaller groupings of stars like the Big Dipper, the Pleiades, the summer and winter triangles, and they help us navigate the skies. I'm on a hair trigger now. Some stars have names, and we know many of these as well, but even if we're not sure what Betelgeuse means. We're familiar with deep sky objects such as M42, the Great Orion Nebula, and about 60 dozen other more objects in this picture. But in many ways, the stars are the most mysterious. When we see the Pleiades, we're only seeing points of light. In all the sky, only a couple of stars actually show a disk, and then only with great difficulty and using amazing instruments. So how do we know anything about these points of light? Other than a name, perhaps, and a set of coordinates, there's not been much to say until the advent of astrophysics. This talk will deal with how we know so much about the stars by tracing the history of astronomy in the 19th and 20th century. Specifically, I'll be talking about the HR diagram. It's one of the most important and widely used diagrams in astronomy, with applications that extend far beyond the purposes for which it was originally developed more than a century ago. It has many names: color magnitude, mass luminosity, but the most famous name. Every astronomer has seen this chart. Or a similar one at some time, in a book, a magazine, online, wherever. Many of you are very familiar with all its many details. Some will recognize that it's an HR diagram and think, I should learn more about this thing. And some might say, whatever. For those who have mastered its details, this presentation might not be enlightening, but I hope at least you'll learn a few new things. For the rest of us, what's a Hertzsprung? Who's Russell? What are spectral classes and why do they start with O? B is in front of A, and what happened to C, D, and E? How do you determine luminosity, and how do you take a star's temperature? To explain the diagram, I need to describe how the horizontal and vertical axes were determined. And to do that, we need to review some history. I'll talk about 19th and early 20th century advances. We sometimes forget how brilliant these scientists were as we look down from our 21st century perches. Stellar classification has been and is an evolving story, and I'll discuss that in some detail. The HR diagram will be discussed once the groundwork has been laid and its evolution over more than 100 years will be covered. This is not a presentation on stellar evolution. The HR diagram very much lends itself to such discussion, but that subject deserves a presentation of its own. I'll introduce you to a number of important people. Some of these individuals I'll cover in less than a minute, some a bit longer, but each one plays an important part in the story I'll tell. You may be familiar with every name on this list, but odds are some of them are new to you. And even if you know every name, I plan to present a few facts which may surprise you. We'll start in the 19th century and proceed up to today. In general, I'll go chronologically, but many of these events are intertwined. Science is often a back and forth between new instruments and new ideas. This is a story of scientific advances. It's not a math-heavy presentation. Just because I list a formula or a law doesn't mean I can use it or prove it. I take on faith that the theory or law is correct. Finally, we don't all have the same knowledge levels, so I'll try to use less technical terms when I can. If I'm confusing you or if you have a question, send a chat note or pipe up. I'll try to answer your questions, and if I can't, Mary Lou might be able to field them, or in any case, I'll get back to you with an answer. Astronomy is a unique science. Most scientists get to physically touch that which they study. The biologist gathers specimens, the chemist manipulates various elements and compounds, the geologist takes samples of various rocks, but the astronomer only gets to look. I'll introduce you to Cecilia Payne soon, but before then, the first few sentences of her PhD dissertation sums this up better than I can. Quote, "The application of physics in the domain of astronomy constitutes a line of investigation that seems to possess almost unbounded possibilities. In the stars, we examine matter in quantities and under conditions unattainable in the laboratory. The increase in scope is counterbalanced, however, by a serious limitation. The stars are not accessible to experiment, only to observation, and there is no very direct way to establish the validity of the laws deduced in the laboratory when they are extrapolated to stellar conditions." Until 1969, until 1969, the only things we could touch were meteorites. Since 1969, we've had sample returns from the moon, comets, and asteroids. But practically everything we know about the stars is because we've learned to study and understand the light emitted by these distant points in the sky. Dr. Yogi was right. The information that we glean from starlight is the key which unlocks the mysteries of the stars. The light tells you everything, and this presentation will attempt to show you how. And so I start this presentation from a scholarly perspective, but sadly, only from third grade level.
Steve, is there supposed to be sound for this?
Yeah, and the sound is important. Let's see if we could get the sound going.
Well, the thing is, I can't do anything on my end. It's coming from Steve's computer. When you share, you have to tell it to share the audio from your computer. Steve?
Super thing.
Oh, there you go.
Steve, we cannot hear the song.
I hear you.
I think you have to stop sharing
Yeah, I think
Read.
so.
and reshare and click off, share some sound.
Yeah, there's a little tiny checkbox at the bottom of when you go to share something, and you check it off this little box that includes the audio.
Can you hear me?
Yes, we can hear you fine, but you're not sharing your audio from your computer.
Testing 1, 2, 3.
We can hear you.
But the audio from your computer is different.
Yeah. Okay. Now, when you go to share, there should be a little checkbox on the bottom somewhere that you can check off to share the audio.
I don't believe this. By any chance, can you hear me?
Oh yeah, we can hear you.
Testing 1, 2, 3.
Yep.
We can hear you, but you
Can
are
you hear me,
different from the,
Marilyn?
yeah, we can hear you, but we've always heard you. We need to hear the computer.
Okay, I'm now hearing again. I don't know what that was all about. I apologize. So, shall we try to resume without
Yeah,
the
wait.
music?
Yeah, either without the music or
We'll do it without the music.
or look for that checkbox when you share again. See if you see that little checkbox and try checking it. See if that works. Otherwise, we'll proceed without
Well, we'll
that.
go to share screen and see what happens.
Yep.
Okay. Let's try it without the music. Very funny and clever, but it destroyed everything. A saboteur. Okay. Astronomy is a Greek word meaning the science that studies the laws of the stars. Astrometry is the branch of astronomy that involves precise measurements of the positions and movements of stars and other celestial bodies. In the 16th century, Tycho Brahe used improved instruments to measure star positions more accurately than previously. How good were the measurements? Good enough for Kepler to develop his 3 laws of motion. Have you ever seen a transit telescope? We had one at my college and I used it once or twice for about a minute. More of an old curiosity. Fixed in azimuth and aligned to the meridian, it was used to determine precise coordinates when a star passed behind the meridian crosshair. The parallax method was used to determine the distance to the nearest stars, and Friedrich Bessel made the first measurement in 1838 when he used his heliometer to find the parallax for 61 Cygni and determined its distance to be 10.4 light years. Parallax was difficult to measure. Only about 60 stellar parallaxes had been obtained by the end of the 19th century. And a photometer, such as the one shown here, was used to determine precise stellar magnitudes. This one from Harvard used prisms and mirrors to project 5 comparison stars of known magnitude, so a star's accurate magnitude could be determined. In our modern times, we tend to look down our technological noses at old-time astronomy. But in 1893, the Earth's motions were known to 1/20th of an arc second. Astronomical instruments were accurate to 1/500,000th of an inch. These weren't cavemen. Spectroscopy is the study of how light interacts with matter. I'll be describing how spectroscopy has dramatically added to our knowledge of the stars, specifically its impact on stellar classification. We know that Isaac Newton was the first to show that the colors of the spectrum are contained within the white light by passing a spectrum back through a prism. English physicist William Hyde Wollaston was the first to notice lines within the spectrum, but he was not the person who studied them intensively. Moral to the story, if you make a discovery, let people know. If he had, I'd be talking about Wollaston lines. That distinction goes to Joseph von Fraunhofer, a Bavarian physicist and optical glass manufacturer who invented the spectroscope. He discovered and studied over 500 dark fixed lines in the sun's spectrum. Those lines are named Fraunhofer lines in his honor. He was the originator of the science of stellar spectroscopy. He found that the spectra of Sirius and other first magnitude stars differed from the sun and from each other. And he concluded that the lines originate in the nature of the stars and sun and carry information about the source of light, regardless of how far away that source is. Gustav Kirkoff was a Prussian physicist who developed a number of laws. We're interested in his laws of spectroscopy. I'll just let you look at those for a second, and then we'll go to his picture. Picture's worth 1,000 words. A luminous solid, liquid, or dense gas emits lights of all wavelength. That's the picture on the left. A low density, cool gas in front of a hotter source of continuous spectrum creates a dark line or absorption line spectrum. A low density, hot gas seen against a cooler background emits a bright line or emission line spectrum. A star will create an absorption line spectrum because the continuous spectrum emitted by the dense opaque gas that makes up most of the star passes through the cooler transparent atmosphere of the star. So what happens during a total solar eclipse? The spectrum switches at totality to an emission spectrum. That was how helium was discovered. The advent of spectroscopy was one of the most significant events in astronomy. It was the key to the birth of astrophysics. Photography was also coming of age. John Draper took the first daguerreotype of the moon in 1840, not with the camera shown. You'll hear the Draper name again in this presentation. Combining photography with spectroscopy was a huge advance. We now had concrete data to manipulate, and more than one set of eyes could evaluate what the data meant. One person may note something another person might miss. By the way, glass plate photography was not easy. I did some long ago at my college, and it was a pain. Go to the darkroom and load 2 plates into the plate holder, one on each side. Load the plate holder into the telescope's camera. Pull the plate shield to take an exposure. 1 per plate. Insert the plate shield. Flip the plate holder and repeat. Head for the darkroom to develop and cross your fingers. Try to handle the fragile image without breaking it. Times have changed. In 1872, Dr. Henry Draper took the first truly successful stellar spectrum photograph of a star, Vega, and spectral lines are captured. Incidentally, the negative images you will see are from the Harvard glass plate collection. If you ever want to view a portion of the sky as it was in 1910 or so, that's an excellent source. We don't deal with negatives much anymore. We're too proud of our modern color renditions. Although photographic sensitivity rose steadily, it did not surpass that of the eye until the 1880s. Consequently, the technology was useful only as a recording tool, not as a means of discovery, and it was viewed with indifference by many professional astronomers. Angelo Seki was a Catholic priest from what is now Italy. A trained astronomer, he was the first to authoritatively state that the sun was a star. His main area of interest was astronomical spectroscopy. In 1863, he began collecting the spectra of stars, accumulating some 4,000 stellar spectrograms. He was the discoverer of the principle of stellar classification, a fundamental element of astrophysics. Through analysis of this data, he discovered that the stars come in a limited number of distinct types and subtypes, which could be distinguished by their different spectral features. From this concept, he developed the first system of stellar classification, the 5 Seki classes. Whoops. Come on, baby. Work with me. Seki class 1 are white and blue stars with broad, heavy hydrogen lines, such as Vega and Altair. Class 1A is the Orion subtype with narrow lines in place of wide bands, such as Rigel and Bellatrix. Class 2 are yellow stars with less strong hydrogen lines, but evident metallic lines, the Sun, Arcturus, Capella. Seki class 3 are in orange to red stars with complex band spectra, such as Betelgeuse and Antares. In 1868, Seki class 4 was added when he discovered carbon stars. These were red stars with significant carbon bands and lines. And in 1877, Seki class 5 was established. These were emission-line stars such as Gamma, Cassiopeia, and Chiliac. Now let me introduce you to Dr. Henry Draper and his wife, Anna Palmer Draper. The Drapers began living their commitment to astronomy as newlyweds in the autumn of 1867. Their honeymoon took them only as far as Lower Manhattan to purchase a glass blank, 28 inches in diameter, which they polished and rouged and coated with silver to fashion the mirror of a large reflector telescope. Henry Draper was introduced to photography early in life. His father, John, is credited with the first astrophotograph of the moon. Henry helped him photograph microscope slides. He followed his father into medicine. He completed his education at age 20, but had to be 21 to be a doctor. So he traveled abroad. He visited the Earl of Ross's observatory in Ireland and saw Leviathan, the largest telescope of the time, 72 inches. This inspired him to bring photography to astronomy. He became a doctor and ended up as a professor at NYU and later the dean of medicine, but he was fascinated with the stars. What were they? He became more skilled and took the first image of a nebula, the Great Orion Nebula. He invented a slit spectrograph and improved his clock drives to track more precisely. His goal was simple: photograph all the stars and their spectra, find out what they were. To that end, he retired from medicine, settled his financial affairs so that he could devote the rest of his life to this goal. 5 weeks later, Draper died of double pleurisy pneumonia. Anna Draper had been Draper's assistant for 15 years. She prepared photographic plates for each exposure, and at the beginning, this meant spreading wet emulsion onto the glass plate. They'd spent countless hours in the observatory together, and his death was a blow. She tried to hire assistants to help her at the Draper Observatory in Hastings, New York. She wanted to finish her husband's work, but in 1886, she determined she could not do the work as well as Henry Draper, so she turned to a friend for help. Edward Charles Pickering was the director of the Harvard College Observatory and a friend of the Drapers. Although originally a physicist, he became one of the most prestigious astronomers of his time. He published the Harvard Photometry in 1884. This was the first great photometric catalog. He invented and then introduced the use of the meridian photometer to measure the magnitude of stars. Recognizing that the best service he could render to astronomy was the accumulation of facts, he instituted great research projects, often of a considerable routine nature, so that a sufficient basis in fact could be established for the solution of stellar problems by future astronomers. He enjoyed doing large pieces of routine work and made over 2 million photometric setting readings himself. He discovered the first spectroscopic binary star. Some controversy developed over who the discoverer was, and I'll address that in a minute. Pickering agreed to help Anna Palmer complete her husband's work. Anna Palmer Draper gave Harvard over 15,000 glass plate photographs. She gave them the 2 Draper telescopes and the money to build observatories to house them, and funding for the personnel to operate them, and the funds to pursue Henry Draper's goal. She established the Henry Draper Medal for Excellence in Astrophysics. Anna Draper invested $250,000 to complete her husband's dream, and I would add at this point. She died in 1914, and the front to the Draper catalog, which was published at that time, had this as the frontispiece. The Henry Draper Memorial is due to the unfailing devotion of Mrs. Draper to the memory of her husband. In her will, she gave an additional $150,000 for the ongoing care and study of several 100,000 photographic plates, which are still preserved at Harvard. Her gift to Harvard is at least $11 million when adjusted for inflation, and the Henry Draper Memorial Fund still supports the curator of astronomical photographs positions today. So who made the greater contribution to astrophysics, the skilled astrophotographer or the devoted wife who carried on his dream rather than cleaning the junk out and moving on with her life? You decide. The women who were hired by Pickering to work on the Henry Draper Memorial are now known as the Harvard Computers. There's some very important people in this group, and we'll meet several of them shortly. The story is told in the book, The Glass Universe. I highly recommend this book. It's interesting and inspiring. Computers worked in a simple area, studying and analyzing glass photographic plates. You might note that Mrs. Draper happens to be in the room when this picture was taken. They used a backlight, a microscope or a magnifying glass, and a little thing they refer to as a fly spanker, which was a tiny clear plate which had various magnitude stars on it so they could make quick comparisons. Some of the plates they have. Our first Harvard computer is Henrietta Levitt. She discovered one recurring nova, but she was assigned the simple task of finding variable stars in the large and small Magellanic Clouds. She discovered over 2,400. Now that's a staggering number. Her most important discovery, though, was the periodicity of Cepheid variables. This was one of the great astronomical discoveries, and it's referred to as by some as the Levitt Law. Cepheid variables get their name from the star Delta Cepheid. Delta Cepheid is a pulsating variable star that changes its apparent magnitude from 3.5 to 4.4 with a period of 5.366 days. It was the first such star discovered and has given its name to this class of variable stars. These stars vary in brightness with a very characteristic shaped light curve. Gradual dimming, a more rapid rise in luminosity, over and over with a very regular period. Levitt noticed as she studied Cepheid variables in the Magellanic Clouds that there was a relationship between how bright a star was and the length of its period. The brighter the star, the longer the period. Now, this was a powerful tool. If you measured the period, you knew the star's absolute magnitude. And if you know the absolute magnitude, you can determine its distance. It became a standard candle, a measuring stick for stars. In October of 1923, Edwin Hubble was attempting to find the distance to the Andromeda Nebula, and he was excited to discover a Cepheid variable. He could now determine that distance because he had found a standard candle. Hubble's discovery of the distance to the Andromeda galaxy could not have been made without Levitt's discovery. So how did Levitt find variable stars? Here's my simulation of the procedure. Take an image of the Large Magellanic Cloud. You're looking at the negative image, and this image was taken at Harvard's Boyden Station in Peru. Now find another image of the same object. It could be taken a week ago, a month ago, or 10 years ago. Print a positive image on glass. Now superimpose them. Aligning the dark stars from the negative image with the light stars from the positive. If there's no difference, the image should look like this, totally black. If the positive and negative star images didn't all match, you would get stars bleeding through, and she would flag the potential variables. I'll give you an example as best I can figure out from their actual plates. Here's a picture of the Andromeda Nebula, as it's listed up here. And you'll note the plate number MC27446. Now let's take a look and see what we get. Come on, baby. Okay. Now the computers do their work. Note the color code. They've got various color inks for various plates that they're making comparisons with. There were at least 6 different plates being used in this picture. They also have indicated an asteroid, a possible asteroid down the bottom right-hand corner. We'll zoom in a touch. Every single mark there is a possible variable star, identified for further study. Now, the tediousness of this just defies my imagination. But this is what these women were so wonderful at doing and why they're so renowned. Williamina Peyton Fleming was one of the first computers and ultimately was put in charge of the Draper catalog. She had a number of discoveries, including the first white dwarf. And her major contributions for the purpose of this presentation is the development of the Draper classification scheme. Here's a discovery plate for the Horsehead Nebula. If you're having trouble spotting the Horsehead Nebula, it's right there. The spectra were produced by placing a large prism in front of the telescope's objective. While this did not give the definition obtainable by the use of a spectroscopic slit, it allowed a large number of spectra to be photographed on a single plate and gave sufficient definition for analysis. Fleming devised a system for classifying stars according to the relative amount of hydrogen observed in their spectra. Stars showing hydrogen as the most abundant element were classified as A. Those of hydrogen as the second most would be B, and so forth. In 1890, the first Draper catalog of stellar spectra is published through the Henry Draper Memorial. It lists the position, brightness, and spectral type of 10,351 stars. A quick run through of the Draper catalog. DC's is Draper catalog, and these are the numbers of the stars. Number 1 star. The second column is the Durchmusterung or Bonner Durchmusterung astronomical catalog of the whole sky, compiled by the Germans in the 1860s or so. So star number 1 in the Draper catalog is this star in the Bonner Durchmusterung. If it's in the Harvard photometry catalog, it would have a number, and this particular star is listed as 4259 in that catalog, and on and on. Rate ascension, declination. They started the rate ascension hour of 0 and worked their way across. This star is on 7 different plates. Its spectral type is A. You'll note there are a few H's and a couple E's in here as spectral types. Magnitude, and we'll not worry about residuals. It dealt with subtracting values from one to the other, and it would tell you whether the star was reddish or bluish. I don't know, actually, as an aside, what was more difficult, doing the catalog or proofreading the darn thing. So Antonia Mori was another Harvard computer. She was the niece of Henry Draper. She was the one who discovered that Mizar was a spectroscopic binary. Pickering had told her to take a look at the spectrograph and see if she could figure out what was going wrong with it. She made that discovery that it was a double star. She was a little annoyed when she didn't get the credit for it. That's the way it goes, I guess. She was assigned to classify the brighter stars from north celestial pole to 30 degrees, minus 30 degrees. When her catalog was finally published in 1897, it was the first volume of the Annals of the Astronomical Observatory of Harvard College, credited to a woman astronomer. Mori's system went back to Roman numerals. The earlier system had 16 categories, not all used. Mori's system had 22 groups, but it was worse than that. Mori noted that there are stars with identical spectral lines, but the widths of the lines varied. She felt this was an important distinction. She added 8 divisions to each group. You might think that is bizarre. Theoretically, 176 different classification categories. Some astronomers love this system. For example, Hertzsprung used her data in constructing his color magnitude diagrams. He wrote to Pickering saying, "In my opinion, the separation by Antonia Mori of the C and AC stars is the most important advancement in stellar classification since the trials by Seki. To neglect the C properties in solar spectra, I think, is nearly the same as if the zoologist who had detected the deciding differences between a whale and a fish would continue in classifying them together." Why would he feel this way? Because it appeared that stars with wide, strong, broad lines were dwarfs, and stars with weak, narrow lines were giants. William Wilson Morgan, one of the developers of the MK system of stellar classification, which builds upon her work and which you'll see soon, has said that he considers Antonia Mori, for me, the single greatest mind that has ever engaged itself in the field of the morphology of stellar spectra. Pickering was not pleased. He wanted the Harvard system to be adopted as the standard. He believed Mori's system was far too complicated and a simpler classification system was needed. A little trivia question to think about. And we're going to go right to the answer. Annie Jump Cannon, another Harvard computer. She was featured on the 2019 American Innovation Coin Series. In fact, the very first coin in the series. She was a most honored person. She was the first woman to win the Draper Award. She had 3 honorary doctorates, including one from Oxford. She established the Annie Jump Cannon Prize for Women Astronomers. What did she do? Most of her early work was on stellar spectra was done in the 20th century, and the principal figure in the story was Annie Jump Cannon. She joined Harvard as an assistant to Pickering in the 1890s. She quickly became very proficient at classification, examining several hundred stars per hour. Cannon manually classified more stars in a lifetime than anyone else, with a total of around 350,000 stars. She discovered 300 variable stars, 5 nova, 1 spectroscopic binary. When using a magnifying glass, she could classify stars down to the 9th magnitude. around 16 times fainter than the human eye can see. Her work was highly accurate. She reordered the classification system based upon the surface temperatures of the stars, giving us the basis for the system we currently use. The O class was Seki's 1A class, the Orion stars. The O stood for Orion. B stars were judged to have higher temperatures than A stars, so it is second on the list. C, D, and E were removed from the new system, giving us 7 main categories. But this simple system was far too simple for Annie, who had a very fine-tuned eye for spectra. She added subclasses to the system. There were 10 subclasses added to each type. For example, F0, F1, F2, F3. I can see the difference on this chart between F0 and F5, but you have to have pretty good eyes to be able to see the difference between F0 and F1. Now, this is a one-dimensional system. You classify the star and you put it in a box. The box is labeled O, and there's an assumed temperature gradient, which presumes blue stars are hotter than red. How do we figure out the surface temperature? One source is Wilhelm Wien, who won the Nobel Prize for Wien's law, an elegant equation. It states that lambda max, the peak wavelength of light in a spectrum, is equal to a constant divided by the temperature. In this example, we see the sun's spectrum. Lambda max is 501.7 nanometers. Plug B into the equation and solve for T, and you get the sun's surface temperature, 576 degrees, 5,706 degrees Kelvin. Saha was an Indian astrophysicist who helped explain how stars behave at the atomic level. His ionization equation is far too complex for this presentation, but suffice it to say that it proved to be very useful in defining many of a star's physical processes. It confirmed that the spectrum of any star was governed mainly by temperature, secondarily by pressure, and in a small way by chemical elements. This realization that the physical state of a star could be quantitatively analyzed to its spectrum proved to be a major turning point. He was able to predict where spectral lines would appear as a function of temperature. It was untestable in Earth laboratories, but the predictions matched any jump cannon system. In 1925, an Englishwoman, Cecilia Payne, became the first woman to earn a PhD in astronomy from Harvard, though as a woman, her degree officially came from Radcliffe. In her PhD research, she discovered that the atmosphere of the sun is made mostly of hydrogen in quantities millions of times greater than assumed. Using quantum physics, a relatively new science, and Saha's ionization equations, she was able to calibrate the star's temperatures based on spectral class. Payne's dissertation was reviewed by astronomer Henry Norris Russell from Princeton, who dissuaded her from concluding that the composition of the sun was predominantly hydrogen because it would contradict the current scientific consensus that the elemental composition of the sun and the earth was similar. After all the elements show up in the sun's spectrum. Payne consequently described her results as spurious, but Russell realized she was correct when he derived the same results by different means. In 1929, he published his findings in a paper that admiringly acknowledged Payne's earlier work and discovery, concluding that she was the first person to know what the sun was made of. A few years later, astronomer Otto Struve described her work as the most brilliant PhD thesis ever written in astronomy. So, Wien's law, Saha's equation, and the work of Cecilia Payne calibrated the temperature scale of the HR diagram. What about luminosity? How do you determine luminosity? The first stars plotted were stars of known distance, either by using parallax measurements or star clusters of known distance using parallax or Cepheid variables. If you know the distance and the apparent magnitude, you can determine luminosity, absolute magnitude. The inverse square law Allows us to determine distance if we know luminosity. We can also use it to find luminosity if we know distance. We'll demonstrate its use in a few minutes. Now that we've figured out our axes, we're getting ready to get to work on the diagram itself. But first, a slight detour. Hans Rosenberg was a German astronomer who produced a color magnitude diagram correlating luminosity with spectral type for stars in the Pleiades. You will see an almost identical diagram in a few moments. In this diagram, brightness decreases as wavelength increases. He published this data in 1910. A couple more points about him. Rosenberg became the director of Tübingen's observatory in 1912. He served in World War I, later became the director of the observatory at the University of Kiel. His tenure at Kiel was officially terminated in May 1935 by Germany's new citizenship law, which restricted the rights of German Jews. The Rockefeller Foundation and other charities were able to bring Rosenberg, as well as his instruments, to Yerkes Observatory as a guest lecturer. This allowed him 3 years of respite. However, by then in his mid-50s, with poor command of English and a few publications, he could find no favor with Yerkes director Otto Struve. In 1938, he sold his laboratory equipment and household furnishings to pay for a move to Istanbul, having accepted an appointment to be director of the observatory. 2 years later, he died of a heat stroke. 4 years later, or 4 years after Rosenberg's 1910 paper, Henry Norris Russell published his color magnitude diagram in Nature, based on an address he had delivered several months earlier at the American Association for the Advancement of Science convention in Atlanta, Georgia. The article credited both the tabular data published by Hertzsprung and Hertzsprung's earlier paper distinguishing giant stars from dwarfs. Sadly, there was no mention of Rosenberg's paper on the Pleiades. So now you've heard it here, and in memory of an unknown astrophysicist, I say, gute Arbeit, Hans. I'll tip my hat to you if no one else will. Enyar Hertzsprung was a Danish chemical engineer who became an astronomer. Keenly interested in chemistry of photography, he turned to astronomy in 1902, working in small Danish observatories where he applied photography to the measurement of starlight. In 2 papers published in 1905 and 1907, he showed that a relationship exists between the colors of the stars and their true brightness. He noticed that the reddest stars, classified as K and M, could be divided into 2 distinct groups. They were either much brighter than the sun or much fainter. To distinguish these groups, he called them giant and dwarf stars. This work so impressed Karl Schwarzschild, the director of the observatory at Potsdam, that he found a place for Hertzsprung in Germany. Hertzsprung later became the director of the Leiden Observatory in Holland and studied the Pleiades and the Hyades. And why? Because the stars within those individual clusters are at all the same distance from Earth, or at least within a few percentage points. A bright star is a bright star, and a dim star is a dim star. He published his color magnitude diagram of the Pleiades. He relied on Harvard data for much of his analysis. For those who don't speak German, wavelength on the vertical axis. I'm sorry, let me go back here. Wavelength on the vertical axis, magnitude on the horizontal. The dark points are Pleiades stars, and the empty points are stars in the vicinity. There appear to be about 60 stars plotted. As the peak wavelength increases, the stars become dimmer, going from 3rd to 11th magnitude. Hertzsprung and Rosenberg were using the same data, so the graphs should be similar, but I don't think Rosenberg got the credit he was due. Turning to the other name of the diagram, Henry Norris Russell was one of the most important American astronomers and astrophysicists. He spent his entire career at Princeton, first as a student, then a professor, and later director of the observatory. He turned down many offers to move, including one from Harvard to replace Pickering after his death. He was convinced that the future of astronomical practice lay not in open-ended data gathering programs, but in problem-oriented research in which theory and observation work synergistically. In December of 1913, he addressed the Astronomical and Astrophysical Society. And we'll just read this. Investigations into the nature of the stars must necessarily be very largely based upon the average characteristics of groups of stars selected in various ways, as by brightness, proper motion, and the like. The publication within the last few years of a great wealth of accumulated observational material makes the compilation of such data an easy process. But some methods of grouping appear to bring out much more and definite and interesting relations than others. And of all the principles of division, that which separates the stars according to their spectral types has revealed the most remarkable differences, and those which most stimulate attempts at a theoretical explanation. Here's the scatter plot diagram published by Russell in conjunction with his address. Spectral class at the top, no O stars. Absolute magnitude on the side. These were stars of known distance whose absolute magnitudes were known. They were from 4 moving clusters. The Hyades are black circles. The stars in a cluster in Ursa Major are represented by X's. A cluster in Scorpius are open circles, and the 61 Cygni group are triangles. The boundaries of Hertzsprung's observation of the Pleiades and Hyades are shown. Both Hertzsprung and Russell were convinced there were giant stars, very low temperature and very high luminosity. They show up on this chart as I indicate. Dwarf stars with low temperature and very low magnitude are also indicated. Over 90% of the stars ended up in what was originally called the main series. We know it now as the main sequence. The final object on the chart is a white dwarf, low magnitude, high temperature. So now here we have the Hertzsprung-Russell diagram, almost. Hertzsprung may have discovered the relationship, but Russell convinced the world of its reality. We might add, however, English astrophysicist Arthur Eddington developed the mass-luminosity relationship, which could be used in conjunction with the HR diagram. The less mass, the less the luminosity. The greater the mass, the more luminous, but specifically for those stars on the main sequence. This would include over 90% of all stars. So what do we call it? It doesn't have an official name. The US and British astronomers refer to it as the Russell diagram. Russell never called it that. The Dutch and Danish astronomers called it the Hertzsprung-Russell diagram. And we know Gerard Kuiper from the Kuiper belt. He was a Dutch astronomer who had studied under Hertzsprung. While working in the US, he became incensed that his former professor was not being recognized for his accomplishment. And he fought this battle for years. Subramanian Chandrasekhar was editing the Astrophysical Journal in the early 50s. You may recognize his name from the Chandra X-ray satellite. He tired of Kuiper's rants and declared that henceforth the Astrophysical Journal would refer to it as the HR diagram. So let's build an HR diagram. We'll zoom in. Okay, let me make sure I got this. We'll use the Omega Centauri globular cluster, the largest in the Milky Way galaxy. The analysis is by Hipparcos, and I'll discuss the Hipparcos satellite shortly. We'll zoom into a section of Omega Centauri, and then we'll sort the stars by color. Blues on the left, reds on the right, white, yellow, and orange in between. This essentially is the same as sorting by spectrum. We then sort by luminosity, brightest on the top, dimmest at the bottom. Mass and luminosity are related, so we're sorting by mass at the same time. And we see a familiar shape, an HR diagram. Main sequence stars, red giants high and to the right, bright blue stars off to the left, and white dwarf stars in the bottom left corner. All HR diagrams are the same and they're all different. If you've seen one, you've seen them all, and in preparing for this presentation, I've seen them all. Here's a modern example. We have luminosity on the vertical axis and spectral class and temperature on the horizontal axis. Main sequence giants and dwarfs are shown along with graphic depictions of the sizes. I've highlighted the sun. But in addition, solar radii grids have been added. This would be 1 solar radius. Oh, the sun's on it. What do you know? 0.1 solar radius, 10 solar radius, 10 to the second power, etc. Solar mass grids have been added along the main sequence. Lifetime in years. The sun is 10 to the 10th, 10 billion years. The lowest star in the sequence will never die out. Their lifetime could be 1 trillion to 100 trillion years, and if that isn't forever, I don't know what is. Now, the Harvard stellar classification system does not completely describe the star. It cannot distinguish between stars with the same temperature but different luminosities. In other words, it can't distinguish between main sequence stars, giant stars, and supergiant stars. The Morgan-Keenan luminosity class was added to the Harvard system in 1943, and it was based on the work by Antonio Mori. Remember those thick and thin lines? Arcturus is a K03, a normal giant. The sun is a G25, a main sequence dwarf star. Hipparcos was an astrometry satellite launched by the European Space Agency, operational from 1989 through 1993. The Hipparcos HR diagram has the MK system included, and we'll use this shortly. This particular plot has 22,000 stars on it. Gaia is presently performing its astrometry mission, which is due to end in 2022. 100 years ago, there were 60 to 100 stars in an early HR diagram. 100 years later, 4 million stars within 5,000 light years. So let's go to the Pleiades and do a practical example of what you can do, and we'll look at Maya. Come on, baby, work with me. Okay, using astrometry, we have already determined the right ascension, declination, and apparent magnitude. We don't care about right ascension and declination for this portion of the presentation. Using spectroscopy, we've discovered that its spectral class is B83. It's a blue giant. From the apparent magnitude and spectral class, a little math, and the HR diagram, we can determine the absolute magnitude, the temperature, the distance, the radius, the mass, and the density. So let's go ahead and do that. Here's the Hipparcos plot, and we're going to take our example of a spectral class B8 and plot it here, and it's a B83, so here's the 3 line. So the 3 line is here, and the B8 line comes down here. I might not have made that plot in that position, but I don't know what the fine tuning of the scale is at the top. It may be logarithmic, who knows? Okay. Because we made that plot, we can read on luminosity scale 539.8 times the sun's luminosity. The spectral class B8 gives me a temperature of 10,166. And on the far right scale, I'm sorry, I overshot. The absolute magnitude shows up as minus 1.5. How about distance? The inverse square law. Intensity is inversely proportional to the square of the distance. If you're twice as far from a light, it will appear 4 times as dim. So we plug those numbers in, 3.85, etc. Do the math, we get 117.5 parsecs or 383 light years. Using parallax measurements, we get 380 plus or minus 10. So that's pretty close. So this is a spectroscopic parallax. You knew the spectrum, you knew its luminosity. You can determine its distance. Radius. How do you get the radius? The Stefan Boltzmann Law. Stefan and Boltzmann were 2 Austrian physicists who gave us a way to determine a star's size. We'll go over here. Again, we have luminosity, 4 pi r, there's radius, the Boltzmann constant, and a temperature. Well, we have the temperature already. We've got the luminosity. We can solve for radius or for r and gives you a number of 6.8 times larger than the sun. Mass. From the HR diagram, we have the luminosity again. We calculate the radius. To calculate the mass, there's an equation which can be used. Plug in the numbers and you get Maya as 5 solar masses. Getting down towards the end, density. Density is mass divided by volume. We know the mass. If the volume is proportional to the radius, do that math and we can end up with a density figure of only 1.57 of the density of the sun. So we have all these numbers just from looking at the spectrum and the apparent magnitude of the star. As an added bonus, we can plot it and say it's a main sequence star with an approximate lifespan of 5 billion years. Conclusions. The HR diagram, one of the most important unifying ideas in astronomy. It has applications extending far beyond its original purpose. It can be used to make significant judgments about the properties of stars. It's a work still in progress. We have come a long way. One last thing. The Harvard glass plate collection consists of approximately 500,000 images. Over 80% have been digitized and are available for study. All will be available for study except 1,500 plates. Boyden Station in South Africa took over for the station in Peru to map the southern sky. That was in 1926. In 1939, World War II began. The plates were no longer shipped back to Harvard. In 1944, there were over 15,000 plates waiting to be shipped home. And they were running out of room, and they decided to ship some back. A bad idea. The Robin Goodfellow was torpedoed in the South Atlantic by a German U-boat. All the lives lost, and 1,500 photographic plates. And on that sad note, thanks for bearing with me. Sorry about the technical issues.
Well, thanks, Steve. Very interesting story of the Hertzsprung-Russell diagram. It's really fascinating. There's so many things that you can learn from just one graph, so many different ways of looking at it, So very interesting. If anyone has any questions for Steve, feel free to unmute yourself and ask away, or you can also use the chat box as well if you're here with us on Zoom. And so
I'd like to say something.
Sure, go ahead, Marilyn.
Should know for this particular club, which meets in Montclair, New Jersey, this is where Yogi Berra lived. So we really like, you can observe a lot by just watching.
Yeah, and actually another thing, it occurred to me as Steve was talking about the various personalities behind all this research. He mentioned two people that have a local connection. Of course, Horace Russell was at Princeton, and Henry Draper, his observatory was in Hastings-on-Hudson, which is right across the river from us, right across from Alpine, New Jersey. Right across the river there is where his observatory was. So they're both local boys, so to speak. Okay, does anyone have any other questions about the presentation?
Steve, excellent
Yes,
job.
Chris, go ahead.
Yeah, excellent job, Steve. This was a lot of work. I can see tremendous research that you did. My compliments. That's terrific.
Well, it was fun.
I'm sure it took a lot of time. Is there a possibility that we can get a copy of the presentation?
Sure.
Okay.
I can do that. You mean you just want the slides themselves, or?
Yes, just the slides. Yeah. Yeah. There was a lot of detail there, a lot of information I'd like to kind of pour over a bit.
Yes, send it to Mary Lou and we'll make sure that Chris gets a copy.
I will do that.
Thank you.
Okay, any other comments or questions? If not, we'll move on. Okay, great. So thank you for joining us. As I mentioned, members of the club, please do stick around for our meeting. For any visitors, thanks for joining us. Keep in mind that our meeting in November, our next meeting in November, let's see, I'm not quite sure what the date is, but of course it's the second Wednesday of the month, which would be November 10th. So November 10th will be the next meeting, and our guest speaker will be one of our own members, Omar Radwan. He has had quite a bit of experience in building observatories in his backyard, and he's got two of them now, doesn't he? And so Omar is going to be with us, and he's going to talk a little bit about how to build an observatory, your own observatory. And so that should be really interesting. So please do join us on November 10th. And so thanks for being with us.